Assalamualaikum. We will start soon. Uh, we will start at 8. Gonna wait for others. Kejap. Alright, Assalamualaikum. Good morning. Ohayo. Um, can you hear me clearly or not?
Yes.
Yes, Doktor. Yes.
Yes, Doktor.
Alright. Okay, because lately kita ada network problem, especially dekat UTM. Alright, so for today, we will continue to chapter 3, the next chapter, which is another chapter of diode, which is diode as rectifier. Diode rectifier. Okay. Wait, check. Alright. So before we go further, I would like kita sama-sama align where are we now. Okay. So we are now actually in week 3. Admit. So we are now actually in week nak masuk to week 3. Okay, so today is 29 March, right? So we are in week 3. So suppose kita today is 30 March. Sorry, 30 March. So patutnya we still in chapter 2, tapi kita cepatkan sikit so that we can finish our chapter faster and we can do the revision much longer lah, and do much more exercise and activities and all those things. Yeah. So now we are in chapter 3, and then before we go for the test, which is within 18 April to 22 April, okay, there will be a test for this subject. I would like to have one quiz with you. So, just want to ask you, usually how did your other subject conduct the quiz? Because quiz is not so much longer, I think, around 10 to 15 minutes macam tu je.
Using e-learning.
Oh, using e-learning. So you have to upload. Upload your answer in e-learning.
Sometimes they make like in e-learning, they make like how multiple choices question in e-learning. So we have to answer there.
I
And I
see.
think it is more effective also.
But the
Because
problem with
maybe
e-learning,
because of some our friend that don't have a internet connection. That's why we usually learning.
That's why it's better for e-learning, yeah.
Yeah.
Okay, because some of you have internet connection. I see. Alright, so I will upload them in e-learning for your test. Okay, so, for your quiz, sorry. Then I'm not sure for your test how it will be conducted, because test will be same for all section. So these all lecturers will decide one method so that we will have the same test for all section. Okay, so this one we haven't have the final decision yet. After we have the final decision, then I will let you know as soon as possible. Okay, for the test. But for the carry marks, for each percent, how many each percent you can find in your course information that I have upload in the e-learning as well. Okay, for you to check how much percent for your test, how much percent for your quiz, and all those things. Yeah. All right. So just a quick review with previous chapters. Yeah. So we have this one is forward bias, and this one is reverse bias. Okay, when you want, as I mentioned before, if you want to check if it is forward or reverse, you check with the polarity connection between the PN junction and the V source. Okay, the output, the external source. Right. So if it's the same polarity, it means that it is forward bias. Yeah. If it is opposite polarity, so it is reverse bias. So this two is very basic. And then you also need to know about two types of resistance. Yeah, two types of resistance. Okay, we have forward resistance and reverse resistance. And above all, you need to know how to analyze the circuit analyze. Okay, so I have uploaded the answer for yesterday in e-learning, so you can check the answer in learning. All right. Okay, so now let's look what is diode rectifiers, right? So what is diode rectifiers? Okay, due to ability to conduct electric in one direction, I need to accept this first. Can I have QR code? Ah, yes. Can you see the QR code here? Boleh scan tak? Is it functioning or not?
Cannot, doctor.
Really? Oh, too small.
Too small, daughter. Too small.
Okay, I see. Alright. Okay, wait, yeah. This one is it okay? Is it functioning?
Yes, this one function very well.
Okay, alright. So, come, who haven't scanned the QR code, please. I give a moment for this. Alright, finish, yeah? Is it okay? Finish? Can we go? Semua dah? Alright. So, okay, so again, so diode rectifiers, as we know, diode have the ability to conduct electric in one direction, right? And block current in other direction, right? Especially conduct electric in one direction, it is in forward bias. And block current in other direction, it means that it is a reverse bias. So diode are used in circuit called rectifiers, okay? So what is the function of rectifiers? It can convert AC accumulating voltage into DC voltage. Okay, so that is the main function of rectifiers. It converts the AC voltage into DC voltage. All right. So rectifiers found in DC power supply that operate from AC voltage source. Right. So what is power supply? Okay, power supply is very important in every electronic systems. Okay, so no matter how complex or how simplest the system is, there will be a power supply. All right. So for a basic DC power supply, we actually have a various power DC power supply circuits. So this is the basic DC power supply circuit, right? So DC power supply circuit, the basic, it has transformers, it has diode rectifiers, it has filter, voltage regulator, and also load. So what is load? Load is connection to the device, right? So what is the function of each components? So transformer, the function of transformer mainly it's to scale down the AC voltage. Okay, it will scale down the AC voltage. So the ratio is depending between the primary and secondary windings. Okay, so we know transformer they have two windings, right? And it has the ratio is according to how many these things the
Coil.
yes the coil inside that, yeah, it depends. So it has a variety of transformer. Okay, we have start up transformer, we have scale down transformer, and all we have a variety of transformers. So mainly the functioning of transformer is to scale down the AC voltage, so it depending on the ratio. Okay, next. Right. So next, what is the function of filter? Diode rectifier. So diode rectifier ni, the main function is to rectify the AC voltage. Okay, so it will rectify the AC voltage. It will allow the AC voltage only to flow, the current, yeah, to flow only in one direction. So rectifier also, we have two types of rectifier. We have half wave rectifier and full wave rectifier, where we will look further details in the slide soon. All right. So next, filter. What's functioning of filter? Function of filter is to make sure that the input wave is smooth. Okay, so it eliminates all the fluctuations, all the noise. So that is the function of filter. Okay, so voltage regulator. Voltage regulator is will The main function is to control the noise. All right, after it's filtered, sometimes after filtering, there's still noise exists inside the current flow. So voltage regulator will help to control the noise, okay, to maintain the DC voltage for variations in the input line voltage. All right, so before it goes to the load, so actually what is load? Load ni is the circuit, the input of the device, okay, output from the power supply, input to the device. So before electric comes or electric has flow into your device, specific electronic device, this is what the DC power supply do. Okay, this is what the DC power supply do. And you can see also the wave. The wave after it's moved to the diode rectifier, you can see that it changed the wave to all the positive wave. Okay. For those who just joined the class, I give you a moment for you to scan this QR code. Okay, finish. All right. So next, let's look. What are the types of rectifier? So we have half wave rectifier, full wave rectifier, and bridge rectifier. So we will look into detail what is all the types of rectifier later. Yeah. So basic DC power supply, what it is? Okay, basic DC power supply, it converts 240 volts. Kalau Malaysia 240 volts, which is 50 hertz, AC voltage available at wall outlets. Wall outlets ni socket yang ada dekat walls, our walls, ya. Yang ada dekat our walls usually it is AC form, alright. So basic DC power supply will converts that AC voltage which come from our walls outlets into constant DC power supply voltage. Then only after it converts, then only it will transfer into your electronic device. Yeah. So voltage produced is required to power all electronic circuit or devices. Yeah. Okay. By time I should check the connection. Alright, so basic DC power supply, it can be very complex, it can be as simple as it can be also. So, however, no matter how complex or how simplest the DC power supply it is, it should have and it must have these three components, which is it should have the rectifier, it should have filter, and it should have voltage regulator. These three components is a must in a DC power supply. Right. Next, this is the example of DC power supply. This is the simplest DC power supply example. So this is the AC source, okay, which will connect to your wall outlets. Yeah. So this is the AC source, and this is the transformer. Okay, this is the transformer, this is the primary part, and this is the secondary part. So you can see a transformer, it is not physically connected, it is physically isolated. Okay, dia terpisah, these two things. Yeah, the primary coil and the secondary coil is isolated. All right, so this is the example of the rectifier. Okay, so usually rectifier consists of 4 combination of diodes. Okay, and this is the capacitor and this is the load. All right, so this is how the wave will look like at each component, yeah, at each stage. All right. So let's move further to what is transformer. Okay, so this is just maybe a revision of what maybe some of you already know what this transformer is. So transformer consists of 2 windings. Okay, they have a primary winding. So this is the primary winding, and this is the secondary windings. Yeah. So as I mentioned just now, both winding is not connected. Okay, it has a physical isolation. Okay, and AC voltage is applied to the primary, induce an AC voltage in the secondary. So the voltage, yeah, is induced from primary to secondary. So no current transfer at all between the two circuits. Yeah. So the function of a transformer is either to raising up the voltage, okay, to increase the voltage, or to decrease the voltage. So it depends to the ratio of the transformer. If it is 1:2, it means that it is increase the voltage. If it is 2:1, so it means that it decrease the voltage. If it is 1:1, it means that nothing change. The voltage is same. All right. So the basic formula that you have to remember for transformer is this. Yeah. V secondary, voltage at the secondary, divided by the voltage at the primary equals to the N ratio of the secondary over the N ratio of primary. Okay. So this one, I think you have to remember. Right. So let's look. We have three types of transformer. Okay. We have step up transformer. Okay, if it is step up transformer, it means that the V secondary is bigger compared to V primary. Step down transformer, it means that the V secondary, voltage at the secondary, is much lower compared to the V primary. So it lowering down the voltage. All right. So isolation transformer, it means that the V secondary is equal with the V primary. So nothing changes between the voltage, okay, between the voltage, right? So we have, what is the function of step-up transformer? The function of step-up transformer is to raise up the voltage. Step-down transformer, if you want to lowering down the voltage, and isolation transformer, the functioning is to isolate the power device from the power source. Okay, usually isolation transformer is used in safety reason. Okay, in safety reason, because you want to isolate the power source with the power device. Okay, it is for safety reason usually. Okay, next, let's look into the diode rectifier. So what is diode rectifier? A circuit that converts AC to pulsating DC. So it converts the AC into DC. So it can be either half wave rectifier, full wave rectifier, and we have also another one which is bridge rectifier, which is bridge. Bridge also is the combination of half wave and also combination of full wave rectifier. Okay, but mainly rectifier is between these two, half wave rectifier and full wave rectifier. Okay, so rectifier can be found in all DC power supplies that operate from an AC voltage. Okay, so in order for you to change AC voltage to DC voltage, you need a rectifier, okay, to rectify the voltage. Okay, next, move to half wave rectifier. What is half wave rectifier? Okay, if you want the circuits, basically will looks like this. Okay, this is the half wave rectifier. Okay, half wave rectifier is a combination of forward bias and reverse bias. Okay, so let's look into detail. So first of all, this is how the wave will look like. Okay, at this stage, it means that the source of the voltage source is in a positive form. So in a positive form, so the currents will flow from here. Okay, so it means that the condition of this diode during this stage of waveform voltage, it is in a forward bias diode. Okay, so when forward bias diode, it means that the circuit is a closed circuit and the currents can flow inside this circuit. So it means that the output waveform will also be positive, like this. There is a output waveform. All right. So next, when the output voltage when the source, V source here, is in the negative form here, okay, in the negative form, what will happen? Okay, the diode will be in a reverse biased. So as we learn and as we know, during reverse biased, there is no current flow inside here. So note, yeah, the diode is in an ideal diode. So it means that during reverse bias, there is no current flow at all, okay, during reverse bias. So it means that this circuit is not a complete circuit anymore. It is an open circuit, okay, the currents cannot flow, and at V output here, there is no voltage come up. Okay, so there is no voltage come up at V output. You can see the voltage is zero, output zero during reverse bias. So if you want to combine, yeah, the output voltage waveform, it will look like this. So at this stage, it means that the diode is at forward bias. At this stage, it means that the diode is in reverse bias. And again, at this stage, it means that the AC source is at the positive sinusoidal again. And at this stage, it means that the sinusoidal waveform of AC source is at the negative part. Okay, up until here, is it clear? Or confusing?
Yes, doctor. Clear.
Okay. Okay, up until here is okay. Yeah? All right. Next, for half wave rectifier, how you want to measure the average value of half wave output voltage? Output voltage is here, yeah? How you want to measure the average value of, sorry. How you want to measure the average value of half wave output voltage? So these are the waveform that will that you will have or you will get from the output voltage of the circuits, yeah, from the circuits. So if you want to measure the average value, what you should take the peak here, yeah, the peak amplitude here, okay, and divide with pi, so you will get the V average. Okay, so this is the formula. You take the V peak, the value at the peak here, and divide by pi, and you will get the V average. So V average is usually between here. Okay, V average is between at the maximum peak with the lower here. So this is the average value. Right? For example, like this. Okay, for example, like this. Yeah? 50 volts. Okay, and it's the peak of this waveform. So if you want to measure or you want to calculate the V average, so 50 volts divided by pi, so it is 15.9 volts. Yeah? The answer will be 15.9 volts. So usually, yeah, V average is approximately 31.8% from V peak. Okay, usually it is 39.8% from V peak. So if you want to check your answer is correct or not, yeah, you can also take the V peak here, okay, 50 times 31.8%, you will get 15.9, yeah. Who's just joining? Right. So this value, 31.8 is approximately. This is approximately value. Usually, it is 31.8% from our V peak. Oh, Allahu Akbar. What happened? No. Okay, so usually it is 31.8% from our V peak. It is lesser than our from the maximum output voltage value. Yeah. So next, let's see the effect of barrier potential for the half wave rectifier. So barrier potential, let's take into account that the diode that we use is silicon. So when we use a silicon diode, the barrier potential usually is 0.7 volts. Yeah. So the barrier potential value 0.7 volts will take into account. So first of all, during the positive half cycle, okay, at this stage, positive half cycle, the input voltage must overcome this input voltage, yeah, must overcome the barrier potential of this diode, okay, in order for the currents to flow. So it means that at the output waveform, okay, the value of output waveform will not be the same with the input here. So because there is a barrier potential here, so the value of the output, yeah, will be value at the input here, VP in minus the barrier potential value, yeah, 0.7 volts. Okay. So it is usually acceptable to use the ideal diode model, which neglects the effect of barrier potential. Usually we will assume that the circuit is ideal diode model. But sometimes if you want to be very accurate, you have to take into account, or you have to also consider the value of barrier potential too. Okay. But usually we will neglect this value because it is very small, 0.7 volts only, right? So VP out equals to VP in minus 0.7 volts. Yeah. So effect of the barrier potential. So if you want to draw the graph, so how it will be. Okay, example here. Yeah. So this is the V in, V that comes from the source. Yeah. Positive 5 and minus 5 AC voltage, right? So the solution at the V out, how it will be, so 5 volts minus 0.7 volts, it will give you 4.3 volts, right? So the waveform, if you want to draw the waveform, you should be very careful, okay, where the peak here is no longer 5. The peak here is 4.3, okay? All right. Sometimes in exam, they will ask you to draw the output, the V output waveform. Okay, so please note how to draw the V output waveform too. Right. So next, move into the next one, which is diode rectifier in a full wave rectifier. Okay, full wave form. Okay. So what's the difference between full waveform and half waveform? So full wave rectifier, it allows unidirectional current through the load during the entire 360 degrees of the input cycle. Okay, it's allow unidirectional current through the load during the entire 360 degrees of the input cycle. It allows current to flow during both positive and negative. So during just now, when we look half wave rectifier, okay, half wave rectifier, during negative currents, there is no during negative voltage, there is no current flow at all because the diode becomes reverse bias, right? But for full wave rectifier, it allows current to flow even though the voltage source is at negative, the negative cycles. Yeah, so it allows current to flow both during positive and also negative. Okay, and then the output voltage is twice the input frequency. Yeah, this is the difference between half wave and full wave. Kalau full half wave, the output voltage is same with the input frequency, but for full wave rectifier, the output voltage is twice the input frequency. Okay, so this here the waveform will look like, yeah. So during the positive cycle, there is also positive current or current flow, okay. And during the negative cycle of the volts too, there is current flow inside the circuit, okay. So that's why if you see the input frequency will be twice compared to the the output frequency, the output frequency will be twice compared to the input frequency. Okay, so how to measure the average value of full wave output voltage? So V average, this is how the calculation would be. V average is equals to, I think you don't have to memorize this. This is just to show how you will get this one, right? What you have to memorize is V average is equals to 2V peak over pi. Okay, 2V peak over pi. And usually kalau for half wave rectifier, the value is 31.8 just now, right? But for full wave rectifier, okay, the value is 63.7% of V peak. So it means that the voltage is higher compared to the half wave rectifier. All right. So the average value for a full wave rectified sinusoidal voltage is twice that of the half wave, right? So these are the example of the questions. Okay, V average, in order for you to calculate V average for the V output source here will be 2Vp. So where the V peak, you should take the reading from here, 215 over pi, so it will give you 9.55. So if you compare 9.55 with the 15 of the peak value, it is actually approximately 63.7%. Okay. So RMS value, okay, what is RMS? Root mean square, okay, value of the output voltage. How to calculate? Okay, V RMS square, okay, it is usually V peak square over 2. Okay, if the question asks you what is the V RMS of the output voltage, so V RMS square is equals to Vp square over 2. So if you want to get the actual value of V RMS, it will be square root of Vp square over 2. Okay. So usually V RMS is equals to 0.07 V peak, right? This is just a formula, so there's no other way. You have to memorize these things, yeah. So next, looks like let's look to the next thing, which is the full wave rectifier. It can be divided into two types of operation, which is either it is center tap or bridge. Okay, center tap or bridge. Okay. First of all, let's look at the center tap. What is center tap? Center tap full wave rectifier operation it is a type of full wave rectifier that uses only two diodes. Okay, it only uses two diodes connected to the secondary of a center tap transformer. Okay, so the circuits will look like here. Okay, there is only two diodes connected to the secondary of a center tap transformer. Okay, of the center tap transformer, only two diodes is connected. So that's why it is called center tap transformer, because the location of the diode is at the center of the secondary. Okay, so the input voltage is the input voltage is coupled through the transformer to the center tap secondary. Okay, half of the total secondary voltage appears between the center tap and each end of the secondary winding. I'm not sure if you can understand or not of this statement, but I think you can understand if I explain in terms of how the circuits operate. Okay, so let's look at the positive half cycle. Okay, positive half cycle here. At the positive half cycle here, okay, the current will flow from here at the secondary windings. Yeah, the currents will flow from here to here to the, this is the load resistor. So it makes that the current flow from the anode to cathode, right? So it makes this diode becomes forward bias diode. However, for this part, okay, since the currents flow from here, it will make that the currents input for D2 is at the cathode. So it makes that D2 diode is a reverse bias diode. Okay, it's a reverse bias diode. So it means that D2 the diode is off, and D1 the diode is on. So during at this positive cycle, okay, the output waveform is also positive. Okay, next, let's look at the negative half cycle. At the negative half cycle here, which is here, now the currents flow from here, from the negative source. Yeah, so it means that the currents will flow from the anode of D2, okay, and flow to the resistors load here, yeah, and will come to the cathode of D1, So it will mix now, yeah, D1 becomes reverse bias, and D2 will become forward bias. So it means that there's no currents flow here, and the currents is only flow at these parts, yeah. And another things that you need to take note is the resistor. The flow of current at load resistor is always same, no matter it is a positive half cycle or negative half cycle, right? Right. So another thing that you have to take note is how the waveform at the V output. Okay, so it means from the at the negative cycles, the waveform at V output is also positive because the currents flow, that flow at the resistor load here is positive too. Okay.
Doctor.
Yeah. Yes.
Will from the second flow,
The
second flow,
negative half cycle.
will the current go back to the AC source?
AC source, no. It means that because at this part, right? This part is off.
Yes, because the AC source is negative, right? So the ground is 0. Maybe it will flow back to the AC.
No, because after this, it will. Oh, you mean from here? From here, it will connect.
No, from the starting point.
Here.
From the ground, yeah.
From this ground.
Will it flow back to the AC source?
AC source. How you want to flow back to the AC source? Here, AC source here, yeah.
Yeah.
The ground here. If you see, this ground and this ground is connected. Actually, ground anywhere in the circuits, there is no ground here, right? So it means that this ground and this ground is connected. So it means that in a circuit, right? In a circuit, no matter where you ground, no matter where the ground, it is actually connected, right? Because it will comes, it is connect, it is what? How to say? It is. Macam mana nak cakap ground ni kan dekat mana-mana kita ground pun dia sama, but it will not flow. I'm not sure it is flow back to the AC source or not, because why did you think it is flow back to the AC source?
Because the AC is negative voltage, right?
Negative.
Then usually we flow from 0 voltage to negative voltage.
Zero voltage. The
ground is 0, and then the AC is negative.
The ground is 0. Ground here, yeah. Ground here is 0, and the negative voltage is also 0. So how it will flow back? I'm not sure. It will flow back or not. But I think if the currents still will flow back to the AC source, the value of the current will be not as higher. It will be very small value that you can neglect if their currents will flow back to the AC source. Can you understand or not?
Oh, okay, okay.
In this case, we will take only the majority currents, which is the majority current is flow from here to here.
Okay, I understand.
Okay, then we will take into the we will consider the flow of currents in majority forms. Okay, but then I will check again if the currents will how big or how small the current flow again to the V source. I will check that. Okay, I will confirm that later. All right. Thank you. I didn't notice at all about that. Okay, shall we go next? Next will be the effect of the turns ratio on the output voltage. Okay, turns ratio ni, what is the meaning of turns ratio? It means the turns ratio of the transformer. Okay, in this case, the transformer turns ratio of 1. It means that there is no changing of the ratio. It is 1 to 1. So this is the AC output source. Okay, AC output source that connected to the primary transformer. Okay, and this is the secondary transformer. So how the current, how the wave will look like. Okay, so the wave will look at how the wave will look like at the secondary part of the transformer. At this stage, at D1, okay, at D1, V peak of the primary, okay, V peak of the primary, which is at this level, V peak of the primary will divide into 2, will give you the value of peak at this waveform. All right, and for the negative part, negative VP here, it will take the negative VP primary part and divide into 2. Okay. So usually, V at the secondary windings, it comes and it is originated from the V at the primary windings. So the value is same, but in this case, the value of the V peak for in D1, the value of V peak for D1, it is half of value of V peak of primary secondary. Okay, and the output waveform will look like this. Okay, V output will look like this, where the peak here, the amplitude here, okay, is half to primary value. Okay, primary amplitude here. Okay, so if since that this, we assume this diode is in operational operation, so we take into account the potential barrier value. Okay, so you have to minus the V peak primary divided by 2 with the barrier potential value of the diodes. So this 0.7 value, it might be changed if you use the diode, different diode. Okay, for example, if you use germanium diode, the value will be 0.3. So it is not always 0.7. Yeah. So please note that this one, in this case, the diode is silicon, so it is 0.7. But in, let's say, in the question they use the diode is germanium, so it should be minus with different value. All right. But usually we use silicon. Okay, it's very rare to use a germanium, but there is a possibility. Okay. So V primary is the peak value of the primary voltage. Note that VP secondary is equals to VP primary. Okay, so V output at the VP primary is divided into 2. Okay, minus 0.7 volts, which is from the barrier potential value. And also you can write like this, right? V output is equals to VP secondary divided by 2 minus 0.7 volts. Okay, because VP is equals to VP secondary. Is it okay at this point? Confused tak? Any questions? I hope it's clear. Okay, this is for transformer ratio 1:1. But what will let's look for the ratio of 2, where 1 and the secondary ratio is 2, twice the input power, yeah? Twice the input, twice the primary voltage. So at this case, VP secondary is no longer equals to VP primary. VP secondary is twice VP primary, okay? And the V at the output here, okay, V output here is V primary, okay, minus 0.7. Okay, V primary minus 0.7, right? Or you can also write V output is equals to VP secondary, okay, divided by 2 minus 0.7. Yes, VP secondary divided by 2 minus 0.7. So if you compare the transformer ratio 1 and 2, you can see that V output is always VP secondary, V at the secondary windings, yeah? V peak at the secondary windings divided by 2 minus 0.7. Okay, so like this. Sorry. So if you only remember this formula, it's better because it can be applied at ratio 1 and it also can be applied for ratio 2. Okay, it can be applied at both. Okay, so no matter what the turns ratio, the output voltage of center tap full wave rectifier operation always half the total secondary voltage minus the diode drop, okay, diode barrier potential value. All right. So next, center tap full wave rectifier operation, in how you want to measure the peak inverse voltage, PIV. So first of all, what is PIV? So PIV is the maximum voltage appearing across the diode in reverse bias. Okay, so in the reverse bias, just now, yeah, there is a reverse bias, right? For example, if this is forward bias, this will be reverse bias, right? So what are the maximum? Okay, what are the maximum voltage can appear at the reverse bias condition? Okay, so it determines the minimum allowable value of V breakdown for any diode used in the circuits. Yeah, that is the minimum allowable value. More than that, it will make the diode break. Yeah, the diode must be capable of withstanding this amount of voltage. Okay, so this is how you want to measure the peak inverse voltage. Okay, for in this case, yeah, PIV is equals to VP secondary. Okay, VP secondary at this stage, let's say that the diode is, the diode is, here is reverse bias, and so here is forward bias and here is reverse bias. Okay, so you want to measure the PIV at this bias, at this diode. So how to measure is at VP secondary here, at the anode here, and this is the value of voltage at the anode of the diode, right? So once if you want to measure the value of the voltage at the cathode, you have to minus with the barrier potential value of this diode, right? So that's why the value here is minus 0.7, and then the currents will flow here, right? The current will flow here, but then we know that there is always a reverse current where the flow of the current is very minimal, right? So the flow of the current from here will comes into here. That's why the value is the same, and it should minus with the VP secondary divided by 2. okay, because this currents come from here too. So if you want to measure the PIV, okay, so I think you don't have to memorize all this, the longest part here. Just have to remember this thing. Yeah, PIV is equals to VP secondary minus 0.7. Okay, so since VP output is equals to VP secondary over 2 minus 0.7, so it means that the VP secondary is equals to 2 VP output plus 1.4. Why 1.4? Because this barrier potential is 0.7 and this barrier potential is 0.7, and you have to plus these two. Okay, so I think if you have times, maybe you can try to figure out of this formula to make sure either it is correct or not to get this formula. Yeah.
Doctor,
Mm-hmm.
why is that a VP for secondary or primary we have to divide by 2 because
Why?
of the diet?
Yes, because this one it come from here. Yani. Why we have to divide from by 2? Because yani at this positive cycle here, the currents will flow from here kan? The current flow from here. Sekejap, you need the ratio 1. Sekejap ni, the first one. Okay, why it has to divide by 2? Okay, because the currents, the currents that flow to here, we assume that it's divide macam the currents terpecah dua, it's flow for these two. However, this current is stuck since that this is reverse bias and this is going to be a forward bias in terms of the positive, right? So we will say that the voltage, the voltage of the V peak at here, at this stage, it is divided into 2. Is that okay?
Okay, okay.
Some of the voltage is going to here, but the current is not flow here. The voltage goes into here, but even though the voltage goes into here, but the currents cannot flow here because it becomes the reverse bias. Voltage comes here, currents can flow here because the diode is forward bias. Okay, value of currents is different with the value of voltage. Kalau currents, of course, all the currents will flow here and no current flow here. But for voltage, some voltage will go here, some voltage will go here, but the currents cannot flow here and currents can flow here. That's why. All right. And the total of V secondary total of V secondary here, okay, total of V secondary kat sini is always the same with the total of V primary here. Kalau tambah voltage from here and voltage here, same with the voltage here. Okay, right? So that's why they said here VP secondary is always equals to the VP primary. Okay. All right. Okay, so just now, where did we stop just now? Kat sini. Sini ya. So in order for you to measure the peak inverse voltage here, peak inverse voltage is always 2 VP out. Okay, 2 VP out. Make sure it is not VP primary or secondary. VP out plus 0.7. Okay, VP out plus 0.7. 7. Okay, this is the formula to measure the PIV, peak inverse voltage. Okay, now let's look at the bridge full wave rectifier. Just now is apa tadi? Just now center tap kan? Just now is center tap. Now is full bridge operation pula. So what is bridge operation? Usually, bridge operation it takes advantage of the full output of the secondary winding. Okay. So the bridge rectifier uses 4 diodes. Like just now, center tap it used 2 diodes, right? But for bridge operation, it will use 4 diodes. That's why it will use full advantage of the secondary windings. Okay, macam just now, center tap it will take only half advantage of the secondary windings. Okay, but for bridge it will take full advantage of the secondary windings. Yeah. So current flows the same direction through the load resistor during each of cycles. Yeah. So the current flow is always same no matter what cycle of the voltage is. So this is how the currents, the circuits will look like. Okay, so this is the V source, AC source. Yeah, this is during the positive half cycle. Okay, so during the positive half cycle, so the currents will flow from positive here, right? So currents will flow from here. So current will flow from here. It will mix this D2 and D1 forward bias. This will be forward bias. Okay, since that this will be forward bias, so currents here will be reverse bias, and currents here will be this one. Yeah, currents will come from here to here, and then currents will come here. Will divide into 2 here. So this one is also reverse bias. Okay, so D3 and D4 will be reverse bias. D1 and D2 will be forward bias. Okay, and you can see how the current flow at the resistor load here. Okay, it will flow from the positive to negative. Okay, so this will give you the waveform of the V output. It will look like this, right? So during the negative half cycle, what will happen? The currents will flow opposite way. Okay, opposite way. It will flow from here. Okay, from here. So it makes this diode will become forward bias now, and this will be here. This one. It will be reverse bias, and this one will be forward bias, and this one will be reverse bias as well. And the resistor load here also will flow from positive to negative here. Okay, so the direction of current in resistor load here will always be the same, and the output waveform will looks like this. This is the how the output waveform will look like. Okay, so in terms of during ideal diodes, okay, how you want to measure the bridge output voltage, how you want to measure the value at the output voltage, okay, during bridge operation. So this is during ideal diodes, we need to neglect the diode drops, which is VF equals to 0 volts, right? So during this stage, okay, so it means that for this, since that this will be the forward bias, forward bias, since that the currents will flow from here, right? Flow from here. Someone just joined. Okay, so currents will flow from here, so it will make this forward bias. This is reverse bias. Currents cannot flow here, and then currents cannot flow here too, so this will be reverse bias. Okay, so at V output, if you want to measure the V output, it will be VP secondary, okay, value of voltage, peak voltage of at the secondary winding minus 1.4. Why sorry, this is okay. Y minus 1.4. Sorry. Just now ideal diodes. Okay, the ideal diodes is VP outputs equals to VP secondary because we assume that this diode has no barrier potential at all. So sama saja. VP output sama juga dengan VP secondary. But for practical diode, since that we have to consider the diode drop, which is 0.7 for each diode drop. So since that there is two forward bias diode in the circuit, so it will be 1.4 diodes drop. So the V value of voltage at the output will be peak voltage secondary value, okay, peak voltage at the secondary winding minus 1.4 volts. Okay, this is for practical diodes, right? Okay, so how to measure the peak inverse? Okay, peak inverse voltage PIV for ideal diode. Okay, so for ideal diode, PIV is always equals to VP out. Okay, VP out, because there is no barrier potential ataupun diode drop value is taken into account. However, for practical diode, the VP out, okay, the PIV is VP out plus 0.7, okay, 0.7, because you have to take into account the value of the diode drops or the barrier potential, okay. Next, this is the summarize of the half wave rectifier. Okay, this is the output waveform that you have to know. Okay, for center tap full wave rectifier, this is how the waveform, output waveform will looks like. So which is same like bridge full wave rectifier. There's no changes between center tap and bridge. But the formula for VP output, so VP secondary minus dengan VD, okay, minus dengan VD is diode drops, the value of diodes drop. So it depends, it can be 0.7, it can be 0.3, it depends of the value of diode drops. But for center tap, the value of the VP output is VP secondary minus 2, okay, minus 2, and then minus VD, minus value of diode drops. But bridge forward, for bridge condition, since that they have two, right, two forward bias will be, so it should times 2 VD, all right. And then VL, for you to measure the average value, output value, so it will be VP output, VP out divided by pi, okay. And then for half wave rectifier, for center tap full wave rectifier, 2 VP out by divided by pi, and for bridge full wave rectifier, 2 VP out divided by pi, which is, this is same, okay. And also this is same too. Okay, for RMS, for RMS, this is same, and this is no square root only. So I think this one is very important for you to memorize during your exam. Okay, how you want to calculate the formula, which formula that you want to use. Okay, so if you want to use formula, make sure that you have to first make sure what are the circuits is. It is half wave rectifier or full wave rectifier. If it is full wave rectifier, which circuit or which operation it is, between center tap or bridge. Okay, sometimes in the questions there's not mentioned. This is a center tap operation. They not mention. So what you have to do is you have to identify it by yourself. Center taps only 2 diodes, right? Bridge only used 4 diodes. So that is the difference between center tap and bridge. Okay, and then after that only you can decide which formula you want to use, right? Okay. For VD, you have to identify too what are the diodes made of, right? Either silicons or germanium. Okay, next, let's go into power supply. What is power supply filters? Okay, the power supply filters helps to eliminate the fluctuations. Fluctuations ni sometimes your output voltage tu ada fluctuates. It is not as smooth as you hopes it to be. Okay, sometimes there is a fluctuation due of noise or due of other sources. Okay, so power supply filters will help to eliminate, to decrease all these things out in the output voltage of a half wave or full wave rectifier. So it will produce a constant level of DC voltage. Okay, so it will make, since that there is no fluctuation, there is no noise. Okay, it makes the DC voltage become constant, become stable. Okay, so it is very necessary because electronic circuit require constant source of DC voltage. Without constant source of DC voltage, the electronic circuits will not function as good as it will be. And current to provide power and biasing for proper operation. So filters are implemented with capacitor. Okay, usually there is capacitor inside the power supply filters. So these are the what circuit will looks like. This is AC signal to pulsating DC. Okay, to pulsating DC without filter. Okay, you can see that the wave is like this, right? The full wave will appear. However, with a filter, AC signal to pulsating DC to ripple DC. Okay, with a filter where it's connect filter at this part, it will reduce the large voltage variation. If in these terms, even though the waveform is look very nice, right? But there is lots of voltage variation. Okay, voltage variation is too large. Okay, it can be at this, this point, or at any points. So we don't want that in electronic systems or electronic circuits, right? We don't want that. So we want to reduce the voltage variation as much as possible, and that's why we applied a filter. Okay, so that's why when you see when we apply filter, they will cause a ripple where they will eliminate at this part, the voltage at this part. So it will makes the voltage as high as possible, as maximum as possible. So a small amount of fluctuations in the filter output voltage is called ripple. Okay, so this one, if you can see here, they're still not smooth as it's supposed to be. It's supposed to be, kalau smooth tu dia jadi macam ni, right? But there's still like a mountain like this, small mountain like this. So this, we call this a ripple. This we call a ripple. So ripple factor is an indicator of the effectiveness of the filter. If the ripple factor is bigger, it means that the effectiveness of the filter is good. Okay, so if the ripple factor is smaller, it means that the effectiveness of the filter is not so good. Okay, actually our desire, the V output should be like this. Okay, without any mountains and all those things lah. But this is very impossible to achieve, to have. So power supply filters. Okay, capacitor input voltage. Okay, let's look into capacitor input voltage. So capacitor input voltage, just I mentioned just now, usually filters, there is capacitors too with the which connected to the filter as well. So capacitor, as you know, the function, what is the function of capacitor? Where after it's full charge, it can work as a battery, right? It can work as a battery. Okay, so let's look at this circuit into detail. Okay, at this first quarter cycle of the input, first positive quarter cycle of the input, what will happen to this capacitor? Okay, the currents will flow at this part, and this diode will become forward bias. At the first stage, this capacitor will charge. Okay, capacitor is charging. Okay, will takes all the charge here, and you can see the VC if you want to make dia punya waveform at this stage, you can see that by time the voltage ataupun the value of the VC at the capacitor is increasing, okay, increasing until it reach a limit where the V peak input, okay, the maximum of the input minus the barrier potential of the diode value, okay. Okay, so this is what happening at the first quarter, first positive quarter of the input source. Okay, the capacitor is charging. Okay, the capacitor is charging. Next, next, when at the another quarter cycle, okay, quarter cycle of the positive V input source. Now the capacitor is fully charged, okay, fully charged, and the input voltage from the AC source now is decreasing, right? Decreasing. Instead, the voltage here is higher compared to the voltage here. So what will happen? What will happen? This will flow electric. Okay, the capacitor now will flow currents. Okay, will flow currents compared to this because this is much higher compared to this. And since that this is higher, the value of voltage at diode cathode, cathode of the diode is higher compared to the value of voltage at the anode of the cathode. So it will make this bias, okay, this diode becomes reverse bias. Okay, reverse bias. So now the currents flow here, and since that there is a resistor here, okay, there is resistor here, by time the charge inside the capacitor will decreasing because there is a resistor that will consume the charge from the capacitor here. Okay, so by time the value of the voltage inside the capacitor will decreasing, okay, due to the resistor here. Okay, so the capacitor now retains its charge and the diode becomes reverse bias because the cathode is more positive than the anode, yeah, and the capacitor voltage value is decreasing because of the existing of the capacitor resistors, yeah. Okay, next, let's look what will happen during negative cycles. Yeah, during negative cycles, there will be no currents flow because the diodes becomes reverse bias. So during these cycles, there will be no currents flow from the V input. But what will happen? VC, okay, VC will give its charge. Okay, will give it charge instead during this time. Yeah. So by time the charge inside VC will decreasing. Okay. So next, it will comes into the now it will comes into where V in VAC ni will be now it will becomes the value is higher, maximum, at maximum point. So when maximum point, since that the charge inside the capacitor is decreasing, so now the capacitor now is charging. Okay, since that the value here is increase compared to here, so the currents instead from flow from here, it will flow from the V input source here. Yeah, so the diodes now at this point will become forward bias again. Okay, and the capacitors start to charge, and it will increase again until it achieve its limits of the capacitor. Okay, and it will repeat lah. So it means that by time what will happen? It will continue again. Okay, it will continue from here. It will continue again like this, and then like this. Okay, that's why this from here. That's why it will become a ripple. Okay, daripada sinilah datangnya ripple. How it will becomes, yeah, how it will be, right? So now, how to measure? How to calculate the ripple voltage? Okay. Capacitor quickly charge at the beginning of a cycle, as I mentioned just now, yeah, and slowly discharge after the positive peak of input voltage. After the positive peak of the input voltage, where now the diode is become reverse bias. Yeah, so the variation in capacitor voltage due to charging and discharging is called a ripple voltage. Yeah, So during this time, it means that the capacitor is charging, and this is discharging, and then charging again, and then discharging, charging again, and discharging. And that is why ripple voltage is appear. Ataupun boleh terjadinya ripple voltage. Okay. So the smaller the ripple, the better the filter. Okay. So what it means is, we hope that the ripple is smaller like this. Smaller macam ni, compared to kalau dia macam ni, so this is not desirable. Okay, this means that the ripple is bigger. Okay, as shown like this. Yeah, the larger the ripple, you can see, the larger the ripple here, the ripple here. Okay, the larger the ripple here, it means that the filter is less effective filtering compared to here. You can see that the the ripple here is smaller compared to here. Yeah? Smaller ripple means more effective filtering. Generally, the larger the capacitor value, the smaller the ripple. Okay, so the ripple is based on the value of the capacitor. Okay, so the larger the value of the capacitor, the smaller the ripple will be. So it means that capacitor can retain a lot of charge. Okay. Okay, now ripple voltage. Okay, ripple voltage. So this is during half wave. Yeah, during half wave, what will happen? This is how the ripple voltage will looks like. Yeah, during this time, the capacitor is discharging and then charging again and discharging again. But during full wave, we know, yeah, during full wave it is twice intensity. The intensity is twice with the compared to the input. The output is twice compared to the input. Okay, so during this time, okay, during this time, it will mix. Yeah, the ripples becomes lesser compared to the half wave. Okay, sebab during half wave, dekat positive negative cycle, at the negative cycle, the circuit becomes reverse bias kan, so there's no current flow, so that's why the capacitor is discharging. But during full wave, since that during negative cycles also there is current flow, so it means that the currents the capacitor discharge at the moment, only at the moment, and then charging again. Okay, only discharge at the moment and then charging again. So this will make the ripple become smaller. Okay. So this one, yeah, is capacitor discharge rate. Okay. If like this, it means that the discharge rate is smaller. Yani discharge rate dia lama. Okay. So output frequency of full wave twice that of half wave rectifier. So full wave rectifier easier to filter because of the shorter time. Okay, full wave rectifier is easier to filter because of the shorter time between peaks. Yeah, so full wave rectifier have smaller ripple than the half wave rectifier. Okay, so how to measure the half wave rectifier ripple voltage calculation? Okay, for the RMS voltage, it is VR RMS equals to VR peak minus peak. Okay, so peak minus peak to the value from here. Okay, from this peak to this to this minimum value. Okay, and then divide by 2 square root of 3. So the average voltage, this is the what formula, where it is the value is VDC equals to V peak here. Okay, V peak minus, okay, V peak ni you can get from at the V peak ni, okay, V peak ni where you can get at the earlier of the circuits, yeah, where you can at the earlier of the circuit. So that value minus 1 over half. Okay, half VR. Okay, VR ripple, V ripple peak. Okay, the peak ripple, the V ripple voltage. Sorry. Okay. So the ripple factor, how to measure the ripple factor is VRMS over VDC. Okay. So this one, all this value or all this formula you have to memorize. Yeah? So this is for half wave rectifier. For full wave rectifier, okay, for full wave rectifier, it will be like this, right? So later on, I will show to you this is the summarize of the formula. Okay. Okay, any questions? I think the slides ends here. Any questions that you want to ask? Oh, someone asked, divide two. Did I answer this question just now? Go.
Yeah, doctor, I asked because go ask first.
Okay, okay, I
Goes
see.
to first. Go.
Okay. So I already answered, yeah. Okay, thank you. Because sometimes I didn't realize the chats here. Okay, so any questions for our next session? I would like to show to you examples of for this example questions, because this is two lots of formula, right? Sometimes during questions kita dah tak tahu how to apply all this formula, right? So for the next session we will look into sebab 1 hour je kan, next week 1 hour. So we will discuss about the questions. Yeah. So any questions for today? Daniel, no. Sensei, hi. Okaniwa, no, yeah. Okay, so 30 minutes earlier. Okay, so since that we start earlier today, so if there is no questions, so I would like to end the session here. Okay, if you have any questions later, you can ask me, and I will post the recording video later on here on your e-learning. Alright. So for those yang tak ambil lagi kedatangan this one, I think this one is flash today. Alright. So assalamualaikum and thank you. You can have your breakfast. Alright. Bye.